In order to explain wave front, I will give you a very common example. What happens when we drop a stone in still water? Ripples are formed. The point where the stone has been dropped, it works as a source of ripples. Ripple means if I drop, let us take this surface as the water surface. I drop a stone here. Then ripples means these circles are formed. Now, what do we mean by circles on water surface? If we observe any one circle on water surface, it simply means that all molecules of water on that circle are coming up together and moving down together. What does it mean? It means they are vibrating in same phase. This circle we call it wavefront. So wavefront is a surface on which all vibrations are in same phase. Wavefront is a surface of constant phase. Phase difference between any 2 points on a particular wavefront is 0. So all particles on this particular ripple, they are coming up together, moving down together. That is what we mean by same phase. Same phase means they will come up together, they will move down together. So this we call as wavefront. Now, depending on the type of source, we may have different shapes for the wavefront. When I am talking about the water surface, it is two-dimensional surface. So I drop a stone and then circles are formed. So these wavefronts are circular in shape. But in fact, if we take three-dimensional, then a point source will give rise to spherical wavefront. So first you should note down what is wavefront is, and then I shall tell you the shape of the wavefront depending on the type of source. So wavefront is a surface of constant phase. It's a surface on which all particles vibrate in the same phase, or all vibrations are in same phase, because for some waves there may not be particles. When we are talking about the water waves, we have water molecules, but what about light waves? So we have vibrations of electric and magnetic field. So on a particular wavefront, all vibrations are in same phase. Or we can say wavefront is a locus of points having the same phase. Point source will produce a spherical wavefront. If I take a line source means the source producing the wave is like this. So if the energy is transferred in all these directions, then at a particular time, all those particles which receive energy simultaneously, they will be forming a cylinder. So the locus of all those points will be cylinder. So we can say for a line source, the shape of the wavefront will be cylindrical. Then for a plane surface, we may have plane wavefront. But one thing keep in mind, even for a spherical one, if I am taking one particular part, one very small part of spherical wavefront, say for this I take only this part, then this can be taken almost flat and a plain wavefront. Just as we can say Earth is almost spherical in shape, but we see it flat because of the large size. So if the distance from the point source is very large and we are considering only a small section, then the wavefront can be taken as plane wavefront. Now we have dropped a stone at this point and the ripples are formed. These are the ripples. How is energy transferred from this point where we have dropped the stone to the other molecules of water, it is going in all directions. It's in this direction, it is in this, radially outward actually. So this is, the energy is transmitted from molecule to molecule in all directions, radially outward. This is actually how we draw a ray, particularly in case of light. So this is a wavefront, and these lines, they represent the direction in which the wave is moving. For light, this will be ray actually. What will be the direction here? Again, radially outward. For a plane wavefront, if I take this as the plane wavefront, then this will be the direction of wave propagation. So these lines, arrows, tell us the direction of wave propagation, and this is the wavefront. So wavefront at any point you can see is perpendicular to the direction in which the wave is moving. Okay, now we have drawn the wavefronts for point source, for a line source. How this wavefront moves onward and how is it related to the wave propagation? There is a principle given by Huygens. Huygens principle. It is a method of finding the shape and position of wavefront at any particular time. It's a geometrical construction method actually. And what it says that every wave propagates in the form of wavefront. Huygens was one of those earlier scientists who gave wave theory of light. He proposed the wave theory of that light is a wave. So S is a point source, and it is true for all types of waves that waves propagate in the form of wavefront. So it's true for sound waves also, it's true for light waves also. And we call them primary wavefront. So if I take in this particular direction, I am thinking a particular part of this complete spherical wavefront. So every wave propagates in the form of wavefront called primary wavefront. So AB is a primary wavefront. First point, every wave propagates in the form of wavefront. Second, every point on this primary wavefront acts as a source of secondary disturbances. Every point on this wavefront acts as a source of secondary disturbances, which we call as secondary wavelets. So we have primary wavefront, wave propagates in the form of wavefront called primary wavefront, then every point onto it is giving out secondary wavelets. Third point, a tangent to these secondary wavelets at any time gives the position and the shape of that wavefront. Now see how, if I am taking the spherical wavefront, then now from every point on it, we can take few examples, and then we have again spherical wavefronts. We will call them secondary wavelets this time. So, and then we have to draw a tangent to those secondary wavelets to find out the new position of wavefront. So let me draw these arcs. I'll take a compass, pencil, and how much radius should I take? Speed into time, with whatever speed the wave is propagating, multiplied by the time. Suppose this is the position at t is equal to 0, and I want it after time t, v is the speed, then vt radius. This should be taken and then draw arcs. These are all secondary wavelets. They should be complete. I mean, we can make like this. And then draw a tangent. A dash, B dash. So at t is equal to 0, the wavefront is AB, and after time t, the wavefront is A dash, B dash. Initial wavefront and then final after time t. Now, Huygens principle tells us about the method of finding the wavefront at any given time. Okay, now one assumption he made: when we are drawing the secondary wavelets spherical in shape, it will be complete circle if I am taking it on two-dimension plane, circles. But he proposed that the wave is moving in forward direction, so this backward flow is to be avoided. This was just an assumption. He couldn't give the proper reply why it is happening, but he said that the tangent is to be drawn on the secondary wavelets only in forward direction. So this is the wavefront after time t, if this is the wavefront at time t is equal to 0. Now using this principle, we can prove that the angle of incidence is equal to the angle of reflection, and we can also prove Snell's law, sin I upon sin r is equal to n2 by n1. First let me take the law of reflection. This is a reflecting surface. Let us use Mn, okay, and let AB be the incident wavefront. I am taking a plane wavefront, so plane surface is falling onto it. Okay, how can we draw rays? I told you rays are perpendicular to the wavefront, so I can draw ray also. It will be convenient to us basically to see the angle of incidence and angle of reflection. We are used to ray diagrams, so it makes it easier. So this is incident ray, this is incident ray. Okay, and this will be the normal, so this will be the angle of incidence, and this is 90 degree. Ray is perpendicular to the wavefront, so it is 90 degree. So this will be 90 minus I, so this will also be I. See, now this angle is 90. Ray is always perpendicular to the wavefront. If this is 90, this is I, this becomes 90 minus I, and this is 90, so it becomes I. Plane wavefront falling on a reflecting surface. Now, every wave propagates in the form of wavefront, Huygens principle. Every point on the primary wavefront acts as a source of secondary wavelets which move onward with the speed of the wave. So every point on AB will now produce secondary wavelet. Now, see, secondary wavelet from here will go here, but secondary wavelet from here will not go here because of this reflecting surface. It will go up, it will return to the same medium. But since the medium is same, so whatever time this wavelet takes to reach B dash, the wavelet from A will cover equal distance somewhere in upward direction. Now listen again. Every point on this wavefront produces secondary wavelets which move onward. The secondary wavelet from here will move in this direction, from here also, but secondary wavelet from A, it will move up. By the time the secondary wavelet from B reaches B dash, the secondary wavelet from A will cover equal distance in upward direction. Equal distance because it is the same medium. So, how can we find the reflected wavefront or the wavefront when B is at B dash? Take this much of radius and draw an arc. Let me say it is like this. this distance. I have drawn this arc, okay, and then draw a tangent to this from this point. Observe it carefully. How will we find the wavefront when B is at B dash? B is at B dash, A is somewhere up, I draw an arc, and then one part is here, draw a tangent to it. So this is the reflected wavefront. Draw the reflected rays now. Again perpendicular to this. So one is this, one I can draw here. So these are the reflected rays, sorry. And this will be R. So actually this will be R. This is R, 90 minus R, and then R. Okay, so let me name it A dash. So A, B, this is incident wavefront. A dash, B dash is reflected wavefront. Okay, we have to prove now that I is equal to R. Very simple steps. Draw this diagram and try yourself. You have to use triangle A, B, B dash. A, B, B dash, and triangle A, A dash, B dash. A, B, B dash. Okay, in this A, B dash is common. This is common. B, B dash is equal to A dash. This is what we have taken. BB dash is the distance travelled by the secondary wavelet to reach here, and AA dash is the distance travelled by the secondary wavelet from A in the same time. And this is what we took. The radius of this was taken equal to this. So AA dash is equal to BB dash. Okay, and then one angle this between the ray and the angle AB B dash is actually equal to B dash A dash A, both 90 degree. Now from these conditions, can we not conclude that I is equal to R? What do we call such triangles? The C, and then I is equal to R. Angle of incidence is equal to angle of reflection. Now let me apply Huygens principle to verify or to prove Snell's law. For that, I have to take two mediums, N1, N2. Let me take N2 greater than N1. N2 greater than N1 means V2 will be less than V1. Second medium is denser. That's the meaning of N2 more than N1. Light travels slower in this medium. That's the meaning of denser medium. Okay. AB is incident wavefront. Okay, now again apply Huygens principle, and every point on AB gives rise to secondary wavelets. They will move onward. One difference with the reflection. By the time, or let us draw incident rays also. Okay. Again, this is I, 90 minus I, so it becomes I. By the time the secondary wavelet from B reaches B dash, the secondary wavelet from A will move some distance in the second medium. It's not going back. It's a refraction. It will go to the other medium. Secondary wavelet from here will move onward in the second medium, but in the time B reaches B dash, this will cover a distance, let me say AA dash, which will be less than BB dash. And what's the reason? Because secondary wavelets in this medium travel slower, because this is denser medium. So now I have to take in R which has a radius less than BB dash, less than BB dash. So this is normal, so I will take a distance less than, let us take this, and then draw a tangent to this from here. Draw the refracted rays. This angle is R, 90 minus R, so it will be R. R, this will be 90 minus R, this is 90, so it will be R. A dash, B dash is refracted wavefront. Okay, this is incident wavefront. By the time B reaches B dash, this will cover a distance which will be less than this because it is traveling in denser medium. Okay, if we flip the mediums, if this medium is rarer than this, then I have to take this distance more than this, and it will be somewhere here. Then this wavefront, instead of being inclined like this, it will move like this. We will draw that diagram too. Okay, now this is R, this is I. I have to find out the value of sine I upon sine R. What is sine I? Now this angle is 90 degree. What is sine I? Perpendicular upon hypotenuse. B dash divided by AB dash. And what is sine R? AA dash upon AB dash. So this cancels out. We are left with BB dash upon AA dash. What is BB dash? V1t, and this is V2t. V1 is the speed of the wave in the first medium, V2 in the second medium. So it becomes V1 by V2, or I can write N2 by N1. What is V? C by N. N is refractive index, C by V. So sin I by sin R is N2 by N1. N1 sin I is equal to N2 sin R. This is Snell's law. So Huygens principle could explain that the angle of incidence is equal to angle of reflection. We could also derive Snell's law, sin I upon sin R is constant for a given pair of medium using this principle. Now, one diagram we can take, if I make this medium rare, all this part remains same, but I want you to draw the diagram because that is very important. Okay, now this is N1, this is N2, but N1 is more than N2. So this is rare. Now by the time secondary wavelet from B reaches B dash, the secondary wavelet from here will cover more distance. So take radius more than BB dash from here, and suppose it comes like this, maybe, and then draw a tangent here. Then A dash, B dash, this will be the refracted wavefront. This is the angle of refraction, Earlier it was going in this direction, so R is more than I. This is R. Derivation can be done exactly in the same way, all steps more or less same. So that's all in this topic. Next we will take the principle of superposition and interference of light.